let's take a quick mental break. Let me show you some findings, medical findings, and then we will try to ask what you infer or what you conclude from those medical findings. So some studies have been run, and the studies say that vodka plus water injures or harms your kidney. Rum plus water injures your liver. Whiskey plus water injures your heart. Gin plus water harms your brain. These are medical studies. Many of you know these names. For those innocent ones who do not, vodka, rum, whiskey and gin are hard liquors. These are not like beers and so on, hard liquors. That is why they mix water or ice with them to drink. So now these studies are there. If you look at all of them together, then what is your conclusion? Which one of them is the most harmful? So if you are very scientific, very logical and scientific, then this is your result. I think there is something wrong in water, right? The one item which is common in all of these harmful things in health, right? So there is something wrong in water. So in the future, when you want to do something bad, then you can have this type of an argument. So back to our discussion of stable and unstable crack growth. We have talked of resistance, J resistance curve. It is convenient to express the driving force in terms of an applied tearing modulus, right? Remember, we called our tearing modulus TR for the J resistance curve. So now for the driving force, the opposite, applied tearing modulus T applied. And it is very similar, E upon sigma naught square dJ dA based on delta T, where delta T is the total remote displacement. Remember, right, there is that V notch type of a standard sample. You are applying the load in mode 1 loading. So with the remote load of sigma, what is the total delta? The total delta, right? So delta T is that total remote displacement. It is defined as delta plus CMP, where CM is the system compliance. It is again the compliance. Remember, we have done it many times earlier from chapter 2 until here. The slope of the driving force curve for a fixed delta T is identical to the linear elastic case, except that G is replaced by J. So this is brilliant. I mean, again, huge amount of research and derivations and confirmation and so on must have gone before this final conclusion, that when we did G, now we are doing J, right? So dG dA, this time you have dJ dA for a fixed amount of delta. So the equation is very similar, but in everywhere in the equation, just change G by J. So this is partial, right? Del G del A, del J, right? And this is for load, this is for a given crack size, and this is the compliance and so on. And delta is, right, the normal displacement that you can measure, and delta T then you calculate from here. So once again, we are skipping all the derivations and a lot of physics and mechanics and how do we do the equilibrium equations and so on. But after that, you come to this stage. Okay. For load control, when we are leaving the displacement uncontrolled, right? We are giving the load from 1 kilonewton to 2 kilonewton to 3 kilonewton, but we have left the delta uncontrolled. So for load control, CM compliance is infinity, so that the second term in the above equation vanishes. You go back to that equation and you will see that if you put Cm is equal to infinity, then the second term vanishes, because if it is 1 upon infinity, then it is 0. So dj dA for a given amount of delta t equals del j del A under load control. So this is for load control. For displacement control, it will be the opposite of this. Cm will be 0. Cm will be 0 for displacement control. And the delta t, if you go to the delta t equation, will become only delta. So displacement control, Cm will be 0 and delta t will be equal to delta. And when again you put these equations in the previous, then you will find a dj dA for displacement control. Now conditions during stable crack growth, remember we had conditions of stable and unstable crack growth earlier in LEFM, now in EPFM. So these are J is equal to JR, we understand it very correctly, right? That the J integral, the driving force and the J resistance are equal, and the T applied, which is the T for the driving force, is less than or equal to the T for the resistance, right? So as long as this is less, this means as long as the rate for the resistance of the material is more, then we are stable. So this is very similar to the earlier things that we did in LEFM. And unstable is that when this applied T is greater than the resistance T. So the conditions and so on are very, very, very similar. And because we have already said that the way we have defined J is that we take it to be the same as G, but G was for LEFM, you take J for EPFM and you do the same things. And again we are reminding ourselves that in chapter 9 there is a practical guide on assessing structural stability with these equations and the other equations and so on, right? So if somebody goes to a higher level of work where they want to study the stability and instability under J integral, then chapter 9 will be a place to go. So with that background, let us try to do an example. And again, it is the standard DCB specimen. So derive an expression for the applied tearing modulus in the double cantilever beam specimen with a spring in series assuming linear elastic conditions. So now this is very good. The conditions are linear elastic, not elastic plastic, but we want to find the applied tearing modulus. So this diagram is exactly the same. You have a double cantilever beam type, half height is h, the crack size is a, the displacement is delta, and the thickness of this specimen is capital B. But because we are doing the applied tearing modulus, so with this delta, the total displacement is delta T and the compliance of the system is Cm. So again, right, we have to find an equation for the applied tearing modulus, So go back to the previous pages, look at the equation of the applied tearing modulus, and look at any of the other previous equations, and Cm is there, delta T is there, delta is there, all other things are there. And we know that this time we have linear elastic conditions. So technically we should do G and K1 and so on. But for this linear elastic case, just to be strong mentally that we can handle J, we are doing the applied tearing modulus. So please pause my lecture, take your pen and pencil, go back to the previous pages, derive this and take whatever time, 5 minutes, 10 minutes, but do not give up unless you have done your solution. And go to the lecture notes or go forward in the video lectures only once you are certain in your mind that you have really done it. So if you are coming to this page, then it means that you have already solved it, and right. So now because it is linear elastic, we know that G is equal to P squared A squared upon B EI for the double cantilever beam, right? And delta is equal to 2P A cubed upon 3 AI these two results we have done earlier, but the only thing is that J is the same as G if it is linear elastic conditions. Okay, so therefore in the equation for the tearing modulus, when you do all these del J del A for constant load, so this is J, find the differential with respect to A only, right? So this P squared upon B EI is there, differential of A squared becomes 2A, as simple as that. So this is this. Similarly, del J del P with respect to A, right, with respect to A. So is it with respect to P, if it was with respect, right? So maybe one way or the other, in one there is P squared and this is 2A, in the other it is A squared and it is 2P, right, 2P. Then del delta del A with respect to P. So P is there, differential of P goes away, right, is it, under load control? No, let me go back, I was trying to confuse you, right? Let me go back. This is for load control, P, but you are doing del J del A, so differentiate with respect to A, so A squared becomes 2A. You are doing del J del P, so differentiate with respect to P, so this becomes 2P. So here you are differentiating this with respect to A, A is A cubed, so this will become 3A squared, right, 3A squared. So 3 and 3 cancel and then you have this, and this is with respect to P, and with respect to P only the P goes away. So these are the four quantities that are there in the equation. And now you just substitute them. Why did we find all these? Because the dJ dA had all these, del J del A, del J del P, right? So now you substitute all of them in this equation, and then the T applied is this. So just substitute everything and then you have the T applied equation, right? So as always, if there is any problem, read it carefully, find the knowns and the unknowns, go back in the lectures and so on, see what are the applicable equations, look at the equation, do whatever is required stepwise. Maybe it looks complicated, but it is very simple, and then just substitute into the equations and find your result. So, right, so if you do it like that, you are always very confident. And unfortunately, we do not have a lot of solved examples and so on, because this is a higher level. But whatever we are solving is actually a sort of derivation also, right? So you are becoming good in your simple math, algebra, this, that, plus you are learning the course, right? So with that, there is this great news that this is the end of the chapter as far as we are concerned. Of course, there is much more in elastic plastic fracture mechanics than this, and if you go to the book, you will see that there are many topics which I have not fully covered. But as a basic course, an introduction to fracture mechanics, you have done the very basics from earlier courses, the linear elastic fracture mechanics from, at this level, and now the elastic plastic fracture mechanics. So like elastic plastic means CTOD and J integral, two major things. So without doing major mathematics, we have covered how they are derived, how they are defined, how they are practically measured and so on, what is their relationships, and what is the stability, instability, the JR curve and so on, right? So we will see you next time, and for the time being, thanks a lot. Masalama.